good equipment. So can I have my slides, please? I will start introducing some of the work we do in the center, and then there will be some of the people in my team speaking about their work a little bit more in detail. So if you tune in a little bit later for the people online, this is the inaugural symposium from the Center of Bionics and Pain Research. My name is Max Ortiz Catalán. I'm the professor of Bionics at Chalmers University of Technology and the founding director. So we'll have several talks today. In the morning, it'll be members of the center, and in the afternoon, there will be invited speakers from different countries with whom we have done some collaboration, or we continue doing some collaboration. Just so you know, the questions, because this is a hybrid event, they all going to be addressed using a Slido. So if you want to ask one question, even if you're in the audience, please use a Slido. You can go online and use that code, and then we can get the questions. That's so we don't pass the microphone around and so on. We're still in a pandemic. So this is going to be for the whole day. And the information on this is also on the website, so you can see that. So a few years ago, when I started at Chalmers, we began with a research lab called the Biomechatronics and Neurorehabilitation Lab, and we have had for many years a very close collaboration with Sahlgrenska University Hospital. And now we realized we're having good results, but we thought we definitely would have something better for the patients and for all the stakeholders if we get closer together, and that's why we moved into the hospital now, or since last year, to create this Center for Bionics and Pain Research. And as you hear before, we able to do this thanks to the funding and the support of the Promovilio Foundation and the Lundberg Foundation, and of course we have additional grants from Vetenskapsrådet, the Swedish Research Council, Vinnova, the European Union, and SSF in Sweden. So our mission is to develop and clinically implement technologies to restore function after sensorimotor impairment and to alleviate pain after sensorimotor impairment. And we try to make a lot of emphasis between just developing and the clinical implementation, because to me there's not much point of doing something that's not going to be used. And I think it's very sad when research projects go on and the research funding is over and the whole thing is over. So for that, we're trying to get close to all the stakeholders and the final user to make sure that what we are doing is going to be actually useful and it's going to be approved, because it's not only a matter of being useful, it has to get into the system. So we need to play within a system, the healthcare system that approves certain treatments, and there's evidence that needs to be shown for the system to accept it. So we need to know the system and be with all the stakeholders to be able to do that. So there are three motivations for this center. The first one, as I said, is that we develop technologies with the patient at the center. That kind of makes sense. So for that, we have scientists from the engineering and medical backgrounds. We have support from engineering and surgeons and therapists. And then we have additional support because there's a lot of research going on here. So we need to make sure that we have all ethical approvals and things are done according to the legislation. The second motivation, as I said, is that we managed to cross that difficult barrier of clinical implementation. So when we develop something, we get it to be used and accepted in the system. And for that, we have collaboration with the healthcare professionals to see what will be needed for the system to approve. The center has a board, and the advisory board of the center is made by the heads of 3 departments at Sahlgrenska, Dr. Anna Nilsdotter of the Orthopedics Department, Karina Reinhold of the Hand Surgery and Care Department, and Dr. Peter Dam of the Anesthesiology and Intensive Care Department. And in addition to the heads at Sahlgrenska Hospital, we also have Professor Ulla Rolfsson, who is the head of the Orthopedics Department at Gothenburg University, and Anders Björnman, who is the Professor of Hand Surgery at Gothenburg University, and then Anders Karlström, who is the head of the Department of Electrical Engineering at Chalmers. And because patients need to use devices that have been approved to be used outside in the real world. We're also collaborating with a few industrial partners, with Integrum in Sweden, and then with the two larger prosthetic companies, Osra and Ottobock, and with also some smaller but innovative companies like Princilia in Italy. And finally, the third motivation for the center is that we can provide treatments for complex cases that are hardly found in, we'll say, pretty much anywhere else in the world. So we have managed to bring some of the latest surgical techniques that are available, with also other implantable technologies like osseointegration and implantable electrodes. We, as you can imagine, being a technical person, we have a lot of artificial intelligence for the code and motor volition, and we've done some work on neurostimulation, neuromodulation, and SensoriMotor training. So the idea is that we can provide the best solution for particular needs of patients that have not the standard amputation, if there's such a thing as a standard amputation. And for that, we also have a few clinical and scientific advisors from Gothenburg University and Chalmers in different fields. And we're very happy that we can get the support of our experienced clinicians and researchers. So most of our work is translational. Translational research is very much what we're known for. And from there, there's been few questions that we have moved into more basic or really applied research to find answers to questions that we found out when doing the translational research, and that help us to support the translation to clinical practice. So that's kind of the layout that we have. We're mostly central on translational research, but we try to cover the parts that are needed when they're needed. The center right now has 4 main branches: bionic arms, bionic legs, robotic and virtual rehabilitation, and pain due to SensoriMotor impairment. So we focus on that particular pain either by amputation or nerve injuries, a stroke, for instance. So I will start with delineating a little bit of work on bionic arms. The way I see it, the challenge on replacing a biological arm with an artificial one comes in few aspects. So you need the prosthesis itself, you need the hardware, the motors, and the batteries. And once you have that, you need to find a way to control it. And if you really want to have a good control, you'll have the need of sensory feedback. But all that is not very useful if you cannot attach it to the body. And these are heavy devices. So if the patient cannot wear it and use it, all this is really not very useful. And in a previous talk, conversation with Professor Hargrove, he mentioned that all this also requires rehabilitation. So that's an important part. And the way I see it is the more biomimetic, if you will, is the better the integration between the man and machine, the less the rehabilitation is needed from the viewpoint that if we have a transhumeral patient using biceps and triceps to open and close the hand, it requires learning to adapt to use those muscles to open the close hand. But if we connect into the axons or the nerves or do a nerve transfer, so the patient thinks about closing the hand, and that's the signals that we capture, and that's what the prosthesis is doing, the burden on learning gets reduced. So that's the kind of approach that we are trying to follow, get it as intuitive as possible, as natural as possible. So if we look at the prosthetic hardware, there's a lot of devices now commercially available, and in research, this is basically the only aspect that we don't work with. We collaborate with others that have much more experience on this. We have focused a lot on the control. And when it comes to controlling prosthetic devices, it's about extracting neural information from the patient, understanding what it is, decoding what it means, and then telling the prosthesis what to do. And this can be itself divided in few things. It's the sources, where we get that from. We get it from the brain, from the nerves, from the muscles. How do we get it? The standard way is using electrodes, but if you use optogenetics, for instance, you will have a different kind of sensor. Then for that, you'll need electronics that are particular for the sensor and the source that you are getting your signals from, and then there's a bunch of algorithms to make sense of that. And each of these subjects, you can do a PhD, and there are research labs focus in each of these areas, because these are difficult problems. So the standard way of doing things is to put a bipolar electrodes, 2 electrodes in a muscle. You do a differential measurement, you extract the component of the action potentials, and then you get this EMG signal that drives the prosthesis. An alternative for that will be to put an electrode array and look at every motor unit potential that comes, and that will give you a different or more information from what's happening there. But the clinical implementation of this kind of technology is still on the way. The standard of care is use differential measurement with electrodes. And then you can use more than one pair of electrodes and use algorithms to decode intention of movement, and in principle decode if I will lose my hand there at the level of my wrist, I could still decode every finger movement, and I could do simultaneous control on myself, and my group and many others around the world have done a lot of work on what is known as myoelectric pattern recognition. And for that, there are a bunch of different algorithms, and we have a look at the complexity of the problem and how it looks on the feature space and so on, and we release all of this work in an open source platform that you can go and download, and it's for free, and you can do exactly what you saw in the videos. We also release an open source platform hardware to record EMG signals, and this has been used a little bit everywhere. So this platform also includes computer-based evaluation tools to see how accurate these algorithms are, and we also look at signal processing that it runs in the computer real time, but also in embedded systems. However, algorithms will only take you so far. There's only so much you can do with signal processing and artificial intelligence. The sources kind of matter, and the electrodes as well. So if we look at the electrodes, we realize, and the field has realized for a few decades, that if you go implanted, you have better signals and you have access to more signals, and then you can also go to the nerves. And we have done some work to optimize neural interfaces for recordings. And the good thing about neural interfaces is that you can stimulate and produce sensations, which brings me to the part of sensory feedback. And when we talk about sensory feedback in prosthetics, most of the time we talk about somatosensory feedback, tactile sensations and position of the joints. Patients get a lot of visual feedback when they're using the prosthesis, and auditory feedback. They get to learn how the motor sounds when they are activating it, but this is, as I said, not very intuitive. So we know since the 60s and 70s that if you put an implanted electrode, you get better signals for control, and if you put an electrode in a nerve that was caught by an amputation and you stimulate it, the patient will feel sensations coming from the missing hand. We know this works as a proof of principle since the 70s. However, the clinical implementation of these technologies has not been so successful. So if we look at the problem, we say, okay, we can go with implanted electrodes, and then we can have a wireless interface. This has been explored, as I said, in different ways. You can have a percutaneous lead. The problem is that it's not very stable over the long term, and you can try to do a wireless interface, but we're still waiting to see a clinically implemented wireless interface today. They are about to come, but it's been taking quite a bit of time. There are problems related to power and how much bandwidth you can transmit with the wireless communication. An alternative for that is to use a wire communication, and in this case, what we've been doing is use an osseointegrated implant that we know is a long-term stable percutaneous interface, and we redesigned that to drive the signals from the implanted electrodes to the prosthesis. And an advantage from doing that is not only the communication, actually initially was because one of the major source of problems for people with amputations is the attachment via socket. And this might be a surprise for the engineers that are looking at this, but the main issue is not sensory feedback, it's not the control, is that the attachment of the prosthesis is painful, and they don't wear it all the time. And if they get home and they know they're not going to use the prosthesis, they take it off. It's just very uncomfortable. So this was addressed a few years ago with the discovery of osseointegration in Gothenburg. Osseointegration was discovered by Professor P.I. Brunnemark in the 50s. Dental implants were first used in the 60s, and then this technology was used for attachment of limb prosthesis in the 90s. And a lot of that work has been done by Dr. Richard Brunnemark and Dr. Kerstin Hagberg and many others at Sahlgrenska and Gothenburg University. And Dr. Brunnemark will speak later today about osseointegration. And Dr. Jonathan Forsberg will speak about the osseointegration program at the Department of Defense in the US also this afternoon. So when I joined the field of prosthetics, my work was centered around getting this technology of osseointegration and looking at the neural interfaces and connecting those two so we can develop what we now call the neuromusculoskeletal or neuromusculoskeletal, depending on where you're from in the US or England, prosthesis. So it's a connection between the machine mechanically but also electrically. The control system of the human being the nerves and muscles, with the control system of the prosthesis being the electronics. So with these, we addressed three of the main problems in prosthetics: the control, the sensory feedback, and the attachment. And the first patient that had this technology implanted was done in January 2013, and you probably hear a lot about this. There's been a lot of media attention on this project. We needed if you look at this picture, proximally close to the body is all biology. You start going more distally, farther away, then you see the electrodes and the electronics. And those electronics allow us to record signals, control the prosthesis, but also stimulate the nerves so the patient can perceive sensory feedback. And it's a sensory feedback the patient has been using in activities of the daily living for many years. We have this patient participating in the 2 editions of the Cybathlon. If you're not familiar with the Cybathlon, I'll recommend you to go and Google it. It's a very interesting and I would say motivating competition where technology is used to overcome disabilities. And there are different kind of races. And our patient was the only one who was using implanted electrodes to control the prosthesis. And we basically didn't have to do anything between him, so he basically flew from his daily life and then went and did the competition. We didn't have to tweak anything about his prosthesis to be able to participate. And this is basically, or probably the major contribution of our work to the field is that we can have a interface that allows for the clinical implementation of implanted electrodes in activities of the daily living. And this was, of course, thanks to the close collaboration with medical professionals and engineers, and this has been going on for a few years now. But this patient had a simple hand control and one sensation on sensory feedback. So how do we get to extract more information? So if we see that we're limited on the electrodes, we can look at the source. And the source in this case will be the brain, which is rather tricky on amputations. You have all the information you need on the periphery. So what you can do is surgical reconstruction. And one technique is to do a nerve transfer to a muscle that is in the stump. It's called targeted muscle reinnervation. You can take the nerve that was severed for the amputation, split all the fascicles, take a free muscle graft, put it in each fascicle, and then wait it for growth, and put an electrode there, and that's called regenerative peripheral nerve interfaces. And then you can also take a vascularized piece of muscle and use it as a target. That's the BDMT. And similarly, you can do for the sensory side and have other interfaces to provide sensory feedback. And we're going to hear about some of these surgical techniques later today in this symposium. So we have done a couple of patients with the Neuromusculoskeletal Interface and TMR. And here we've shown that these patients are able, again, to use this technology for several years in activities of the daily living, basically in whatever they are doing. As you can see, the prosthesis is self-contained. The patient doesn't have to carry a backpack or additional battery packs. He takes the hand, put it on the implant, gets mechanical and electrical connection, and then he's ready to go. And this works independently of the environment. If it's very cold or it's very warm, it doesn't really matter because we don't have the skin as an interface anymore. And we have looked at the psychological and sociological aspects of living with this, what you can say, very integrated human-machine interface. And we found that, of course, there is an improvement function, but also self-esteem. Patients get to participate in more activities, a wider range of activities, and they report to see the prosthesis as part of their body. And what does this mean? So there's something called embodiment, and right now it's a bit of the Wild West when it comes to the definition of embodiment. Everybody uses it however it fits them better. We subscribe to the idea of embodiment as made out of 2 senses: the sense of agency that makes you feel that you're in control of something, and the sense of ownership that makes you feel that that something belongs to you. And we see that those two come together in a continuum of embodiment, and depending on how much you have of those two, you will have more embodiment. And the perfect example will be a human hand. However, this is only relevant in a context. And that context depends on how much interaction you're having with the environment. So if you take the rubber hand illusion, when there's no interaction at all, but you have appropriate somatosensory feedback, you can feel like you own a rubber hand as long as you don't move. If you start moving, the illusion breaks. And then you can have that with different tools. And we can say that these patients feel that the prosthesis is part of themselves as long as they are doing this. But at the moment that they will try to do this or do something more complex, then that illusion will break because the interaction with the environment will be higher. So this, and why we care about this? We care about this because we want to create devices that are transparent to the user. So the best assistive device are like glasses. You don't feel you have them. They just work all the time, because if you feel you have them, it's because they're not working very well. So for that, we're developing methods to measure objectively the sense of agency. We've done some work to try to measure better the sense of ownership, but we've found some hiccups with the rubber hand illusion. But we found something very interesting. Most patients with amputations feel like their stump is colder than the contralateral. And this is because the thermal regulation might have changed because there is no limb, but there's also an idea around that it might be related to the embodiment. The brain might realize there is no arm there, it will reduce the metabolic efforts on the limb. And something that we notice with our patients is that they report to have the same, the stump is no longer cold. So the asymmetry, the thermal asymmetry between the arms was reduced. And then, because we didn't test this before we put the implant, something that we try and we're investigating now is we remove the prosthesis, and after that we see that the temperature drops, and then we would put the prosthesis back again, the temperature goes back to normal. So we trying to investigate if this could be an objective measure of embodiment that tells, at a subconscious level, the brain of the patient accepts this prosthesis as a part of the body, and that reflects as changes on the temperature of the stump. So that is one way to get more signals using TMR, and as I mentioned before, with TMR you can get 2 to 3 degrees of freedom. An option that we've been exploring now is to mix in TMR with RPNIs. So we did one patient in which you take the nerve, you split it in two, half goes to a TMR, the other half gets further split, and then we did RPNIs on those. And the reason why we want to do that is because at the high amputation level, we can extract more signals for control. And now we get in there, we're getting at the transhumeral level to have individual control of fingers of a hand, and simultaneous control of different degrees of freedom. Now this is early days, we're trying to get this to be reliable enough to be used in daily life. In this case, the prosthesis is on a table, the patient is sitting. If we get the patient to be moving around with the loaded prosthesis and still be able to do that, then we can say that we achieved something. But at this point, we can see that we can get some information to be able to drive more degrees of freedom of the prosthesis. We're also looking at what we can get directly from the nerves. Recording from nerves is very difficult, but we have some early indications that we can extract even some useful information directly from the nerves using the neural interface to achieve higher control. So that's the work on transhumeral amputations above elbow. We've done the same in the transradial level thanks to a European project called DTOP. And this is the first patient who's using a hand designed by Princilia. So it has sensors in the thumb, in the index finger, and the middle finger, and there she's feeling the softness of those objects that they look the same, but they feel different, and she's sorting them out based on how they feel. So this was, again, a collaboration between surgeons and engineers to be able to implant this device, and all the development that we're doing required a different or a more advanced embedded system that is smaller than the transhumeral. So it's shorter and smaller, so it can fit on a wrist. And this also allows us to produce more complex patterns of stimulation to try to find out different ways in which we can stimulate the nerve to provide better sensory feedback. And some of that we have implemented in some of our patients. We found that, as Lehman will be happy to hear this, that the more biomimetic the algorithm is, Professor Benzmai is going to speak about this a little bit later, to the better their performance. So in collaboration with Johan Westberg at Gothenburg University, we have some discussions with Professor Benzmai as well. We're trying to find ways to improve the sensory feedback with Eric Arley, who's one of the postdocs in the group. So we've taken that learning from the upper limbs and now transforming it or implement it in the lower limbs. So it's a large project. There are many people involved on trying to get that going. We had an early version of the system in an investigation in the AMIS and the Neuromusculoskeletal Interface in the US. We're going to hear a little bit about that later. And the latest version that is designed, the new implant system that is designed for higher activity levels, is now being tested on the bench, and everything seems good so far. And once that's done, we're planning to do the first clinical implementation in a patient, hopefully this year if we have everything ready. We had some delays because of the pandemic. So that's been our work on prosthetics. Something that for many patients is even worse than not having the limb is phantom limb pain. And the reason why I got involved in phantom limb pain was precisely because doing the prosthetic work, I met patients that I said, we're developing this very advanced prosthesis, and do you want to try it? And they were like, look, I'm fine with not having my arms. If a senior person that lived most of his life without an arm, my problem is phantom limb pain. If you can help me with pain, I don't care about not having my arm. And when you think a little bit about it, it's kind of logical, because pain takes precedence over everything else. It's the highest priority. If you're in pain, you don't care about anything else. Of course, once we take care of the pain, they will want to have an arm. But we should try to look at the first priority, that will be pain. So there we're running a clinical trial looking at different surgical techniques and their effect on post-amputation pain. And we try to make a distinction between, so pain can be, or phantom limb pain and pain itself can be multiple realizable, meaning that it can come from different sources. So one of them will be the neuroma, and that's why we're looking at the surgical techniques. And the other one could be more like central changes or maladaptive plasticity. And for that, we developed a treatment a few years ago, back in 2013, that has been rather successful on helping patients with phantom limb pain. It uses some of the technology that we developed for prosthetics, and that we were able to implement it for lower limbs as well. And that went from an open source research project into a commercial product that now is CE marked thanks to the funding of Vinova and the Promobilia Foundation. And since then, we've been trying to improve that system with better electrodes or easier ways for the patient to perform the treatment so it can be used at home independently. So we also shown that this can be done by the patients at home. And because this is a non-invasive platform, it's been relatively easier to translate to different countries. So that means that many patients around the world has now been treated with this technology. And why does this work? Well, the working hypothesis is that we re-engage in as much, or we're trying to re-engage as much as possible the neural circuitry that was affected by the amputation. And as a consequence for that, we have some predictions that will say that probably after this treatment, you will see an expansion of the representation of the stomach in the cortex and a preservation of the other side of the brain. And to test some of those hypotheses and the efficacy of this treatment, now we're running what is probably the largest international clinical trial done on phantom limb pain. I will argue that it's also the most rigorous clinical trial done on phantom limb pain. We published the protocol before we started. We published the statistical analysis plan now, and now we're looking at the results. And we running in parallel some longitudinal studies with functional MRI and EEG, and because when I was trying to make sense of why will this treatment work at all, I couldn't find any of the working hypotheses to be suitable. I proposed a new one called stochastic entanglement a couple of years ago. If you want to hear about it, you should join us tomorrow on the International Conference of Phantom Limb Pain. That's going to be a hybrid event, and we'll discuss that. And what we're doing now is trying to test that by looking at the epidemiology of the data that is available, but also building computational and mathematical models on pain that can help us to understand this a little bit better. So we saw that phantom motor execution is effective in the majority of patients we have treated, but not in the 100% of them. And I would like to have something that is effective in all patients. And if the idea is that we try to re-engage as much as the neural circuits as possible that were affected by the amputation, one way to do that is also to provide sensory feedback. So if we get the control and the sensory feedback going, I believe that we can have a more effective treatment for phantom limb pain, and for that we develop some hardware that allows the optimal stimulation of different mechanoreceptors in the stump, and we are doing a clinical validation of this treatment, and you'll hear a little bit more about this later. We're also interested on the effects of neuromodulation on potential improvements for phantom limb pain. And measuring pain is really problematic, so we're trying to find ways that we can cover it as better as possible. So we have also used some of the technologies that we've been working on the rehabilitation of other conditions. We see that some of those can apply on spinal cord injuries. This is a patient that was diagnosed with a complete spinal cord injury, from which we can still extract some intention of movement, despite that you see that his arm is not moving, yet the virtual arm is moving based on his intention. And something that we're exploring now is in a clinical trial on chronic patients with a stroke, in which we see some promising results. This patient, for instance, couldn't grasp an object before going through the treatment, and now he's able to grab a ball. And this is in chronic stroke patients, so we try to focus on those difficult cases to begin with. We also participated with Dr. Paolo Sasso on the first hand transplantation done in Scandinavia a few months ago, and with this patient we helped the patient to train on the use of the hands in virtual reality, so when she got her transplanted hands, she'll be faster at doing the rehabilitation. So this is another exciting project we got involved with. Because we care about the interface, we also are part of a European project looking at graphene-based electrodes, and with Dr. Maria Absalon, who's going to speak a little bit later, we're also collaborating with some electrodes that she designed on her lab that look very promising. So there's a few people of the group as of today. We're growing, and we're still trying to hire talented people. There is many people who have been involved and still been involved, and we're very grateful for all their collaborations. We collaborate with different institutions around the world, and if you want to look at some of our work on the popular science, there's been a bunch of documentaries done in different languages that you can find in our webpage. I hold a podcast, or I used to, now I got a bit busy, but it's a fun thing to do. It's long conversations with respectable scientists like Professor Besmaya here and Dr. Hargrove, Professor Hargrove. They've been part of the podcast. So that's aimed for medical and engineering professionals. So I think I can take one question. No? We good? Okay. So we were a little bit late because of the delay on the stream. So I think we're gonna jump directly to the next part, so we can have the coffee break in half an hour, hopefully. Oh, well, no, I'm sorry, because we started late, so it's going to be a little bit more than that. Thank you.